Hey guys, it's Angela Swilly, and today we're going to be talking about 9.1 Introduction to Entropy. You need to be able to identify the sign and relative magnitude of the entropy change associated with chemical or physical processes. Entropy reminders. So, we actually learned about entropy in the 7.14 lesson. And sometimes I'm going to put that in Unit 9. Sometimes it may be in Unit 7. But we have already talked a little bit about entropy. Now, an actual chemical system, like a beaker that we put things in or a balloon, contains a huge number of possible sections. And in science, we call these invisible sections the microstates of that chemical system. Now, when the particles or the energy in a system are more spread out into the microstates, we say that the system has more disorder or more entropy. So remember that if we increase disorder, we increase entropy. They are directly related. And the opposite is true. If the particles or the energy in the system are less spread out amongst the microstates, we say that the system has less entropy or less disorder, because if there's taking up less space, they're closer together and they're going to be a little bit more ordered. In simple terms, our delta S, which is entropy, describes the amount of disorder in a system. Entropy increases gradually as temperature increases. This is an important relationship to know. We already know that as temperature increases, the average kinetic energy of particles increases. And increasing temperature, if you think about it, it's when we're talking about that the kinetic energy of particles increases as we increase temperature, that means they're eventually going to be able to, overcome um, the attractive forces that are holding them there, and it's going to cause more disorder. So that's where this kind of comes in with entropy. So increasing temperature will also affect other aspects of energy like molecular vibrations and rotations, electron levels, electron spins, etc. And increasing the temperature increases disorder. So therefore, increasing temperature will increase entropy, since entropy is kind of a measurement of disorder. Entropy increases dramatically when there is a change in state. When a solid melts, there is a dramatic increase in disorder. And that is how we describe entropy, or we can describe entropy with what happens in regards to disorder. When a liquid changes to a gas, there's an even more dramatic rise in disorder. So both of these would be positive delta S's. Entropy increases when substances mix to form solutions. So if we learned 7.14 before this lesson, then you have already kind of talked about this. So mixtures generally have higher entropy than pure substances. And so, for instance, before a solute is dissolved into a solvent, before they're mixed together and dissolve, we have a lower entropy. So remember that dissolving, there can be a decrease in disorder for H2O molecules as they organize around ions. However, the increase in disorder experienced by the solute will ensure that there's an overall increase in entropy. And it shows you on the right-hand side, less randomness is when you have your water and your solute particles, but they're still not dissolved. Once they do dissolve, you have more randomness, more entropy. Entropy increases as modes of vibration increase. So as the molecules become more complex, then the entropy will increase. However, remember that you can have molecules that can vibrate, the infrared part of the spectrum, and rotate, which is the microwave part of the spectrum. More complex molecules can vibrate in more ways and therefore have more entropy. So fewer vibrations, less entropy, more vibrations, more entropy. So the vibrations in the bonds cause it to have more disorder. Entropy increases when a mixture is formed. So this is showing you like a gas, and diffusion is spontaneous, means it happens automatically due to the increase in entropy. We will focus here later when we look at reversible reactions, where a mixture of products and reactants in an equilibrium mixture is inevitable. Entropy increases also with an increased number of moles. Endothermic reactions that are spontaneous are entropy driven. Now, right here we have our reactants, and they didn't have enough room to put them side by side, so I'm just making sure that you know these are the top is reactants and the bottom is products. If you increase your number of moles of gas, well, actually, it's not even number of moles of gas here. We're not talking about just gas, but if you increase your number of moles from your reactants to your products, then your entropy increases also. Oh, and if you'll notice, we have 3 moles in the reactants. I'm sorry, I meant to show you this. It is the 1 that's not written there because it's understood, and then the 2. And then we have 1, 2, 3, and then plus 10 is 13, so 13 moles. So again, when you increase the number of moles, you increase entropy. Entropy increases with increased volume of a gas. Though not as dramatic as the change from a liquid to a gas, the extra freedom to move, rotate, vibrate that is gained when a gas is able to expand into a larger volume leads to more randomness. And you can see that. The more space it has, the more random they're going to be, and that's going to increase your entropy. All right, let's look at this I do. If you want to pause it and try it on your own and resume to get the answer, feel free to do so. For each of the following pairs, choose the substance with the higher entropy at a given temperature. Explain your reasoning. All right, so we have carbon dioxide gas and carbon dioxide solid. So it wants to know which has the higher entropy. So in this one, the CO2 gas has the higher entropy. Since the gas state has particles in a more random arrangement. And remember, more randomness means more entropy. But it has more random arrangement of molecules than the solid phase or state. All right. Which helium gas will have the higher entropy? So the helium gas at 0.020 atms has the higher entropy since at lower pressures, gases will expand, right? Remember, when pressure goes down, volume's going to go up. So they're going to expand to a larger volume. And gases that are expanded have a more random particle arrangement, than those compressed. All right, now let's look at calcium carbonate solid and calcium oxide solid plus CO2 gas. So, calcium oxide and CO2 gas has a gaseous species which has more entropy than a solid will by itself. So, if you see something changing from a solid to a solid and a gas, that means you're going to have more randomness than just the solid by itself. Between a solid, so yeah, there you go. I wrote it all. Okay. I hope you have a great evening, and I'll see you in class.